Okay, chapter 10, number 38 is one that's come up. So let's take a look at what it says. The figure 1032 shows 3.01 kilogram particles that have been glued to a rod of length L is 6 centimeters and negligible mass. The assembly can rotate about a perpendicular axis through point O at the left end. If we remove one particle, that is 33% of the mass, by what percentage does the rotational inertia of the assembly around the rotation axis decrease when that removed particle is A, the innermost one, B, the outermost one? So I sketched out a picture here, like what's in the figure. We have the rotation axis O, the long rod that has 3 particles glued to it, and the length of the rod is L. Wrote down what we know, right? We were given the mass, we were given the length of the rod, and based on the picture, it shows us that all of those particles are separated by a distance d. Because they're all the same distance d, and those fill the entire length of it, then we can know that that distance d is just 1/3 of the total length. So if L is 2 centimeters, if L is 6 centimeters, d is 2 centimeters. So that's pretty good on what we know. What we want to know takes a little bit of untangling from the paragraph. So it says, by what percentage does the rotational inertia of the assembly decrease when we remove a particle? So this is a percent decrease or a percent loss. So I want to think about a change in rotational inertia, I final minus I initial, relative to the initial, and then because it's a percentage, multiplying by 100 at the end there. So that's really helpful to try and get it in terms of what we're actually solving for. Now, we want to think about what tools we have. And the main thing we need is we need a way to figure out our rotational inertia. And the keys here are, they first off tell us that the rod is of negligible mass. That's really great because it means we don't need to consider its rotational inertia. All that we have to consider are these masses that have been glued to the rod. Those are particles, so we can get our total rotational inertia by just summing up the masses times their distances squared. So we'll do that. If we needed the rod, like if the rod wasn't negligible mass, then we could get the total rotational inertia by adding in the rotational inertia of the rod. And we could just add that to all of the particles. But as mentioned, in this case, the rod is considered to be massless or negligible mass compared to these, so we don't need to worry about it. All right, so for adding these together, we want the masses and then their distance from the axis of rotation. So I'm going to do this symbolically, that we have our first one is at a mass times a distance d squared. And then we can add our second one is another mass, and its distance is 2d squared. And then the third one is the same mass m, and it's at a full 3d or just l squared. I'm going to work in terms of d so that they're all in terms of d. Because now we notice that all of them have this md squared term in it, and we can just add the numbers in front. So we have 1 plus 4 plus 3. So that comes out to 14. And that is our total rotational inertia on the initial case. Now for the final, it'll depend on which one we remove. So in part A, the innermost one is removed. So going back to our picture, would be if we took out that first one. And so for calculating the rotational inertia, it's effectively, if we just take out this first one here from the process. So for part A, my I final is just going to be the later ones. So m times 2d squared plus m times 3d squared. Or in other words, 9 plus 4. So it comes out to 13 md squared. for the I final. And so if we take this up to what we want for part A, we would get 13 md squared minus 14 md squared divided by 14 md squared. Fill that in up here. Go. 13 md squared minus 14 md squared all over 14 md squared times 100. And what you may notice is that by writing in terms of md squared, we have md squared in the numerator in both terms and the denominator. So the md squared is actually going to cancel out. We just have 13 minus 14 divided by 14 and times 100. And so when you do that, you should get 7.1% for part A. Okay, so even though we took away a third of the mass, 33%, we only lost 7% of the rotational inertia because this innermost one was hardly contributing to the rotational inertia. But we can double check with the outermost one, which is what we do in part B. So I'll angle this down a bit. So for part B, we are instead focusing on removing the outermost one. So in our previous initial equation, it's going to be this one that's 3d squared away. So that means my final rotational inertia will be the first one, little md squared, plus the second, m times 2d squared. So 4 plus 1 is equal to 5 md squared. And we can do the same process of taking the difference there, where we have 5, I'm just going to do it with the numbers, assuming that they do cancel. 5 minus 14, all over 14. By the way, this does give you a negative result, even up here. The negative is just that it's a loss of rotational inertia. So down here, if you do 5 minus 14, that's negative 9 over 14. That comes out, once you multiply by 100, to a whopping 64%, technically negative there. So even though we only took away 33% of the mass, we lost almost twice the rotational inertia because we took away the particle that was furthest away from the axis of rotation. And this is just like what we saw in lab with the races, where with rotational inertia, it makes a big difference to have mass further from the axis of rotation. That will greatly increase your rotational inertia versus mass close to the axis of rotation doesn't have nearly the same effect. Okay, so hopefully this helped highlight some new or different ideas. If you still have questions, I would love to chat more. So please seek me out.